Well, I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, I thank you for this class and the students. Just ask you to guide our steps today, help us to understand more about solving differential equations this day, Lord. In your name I pray, Lord Jesus. Amen. All right, I will begin with an example. So, example 1. We're up against the problem dy dx plus 1 over x times y is equal to xy squared. All right, so this is an example of what's known as a Bernoulli problem. So, like generically speaking, Bernoulli equation, there's no I there, what's wrong with me? Bernoulli, don't worry, they're dead. Bernoulli equation has the form dy dx plus like p of x times y is equal to some function of x times y to the n. All right? That's a Bernoulli equation. Now, of course, if n is equal to 0, well, then this is just a linear equation, right, which we already know how to solve. But if n is not equal to 0, it's actually a, a Bernoulli equation here. And so the thing to try here, generically speaking, the way to unravel these things, is to make a w equals y to the 1 minus n substitution. That's the way you want to handle these. So let's try that out for my example. So we're going to let w equals to, let's see here, n equals to what? 2. So apparently I'm supposed to try w is equal to, y to the minus 1, or if you like, 1 over y. Now, when I'm making a substitution, I usually find it convenient to solve for y for various reasons. First of all, I'm going to have to differentiate it, right? So if I solve the, y is equal to 1 over w, then when I go to substitute in for dy dx, I don't have to do anything very fancy, right? It's already there in front of me. So this, of course, tells me that dy dx is minus 1 over w squared dw dx by the chain rule. So just to remind you where we are, where we're going, we've looked at all the major techniques of solving first-order problems. Now I'm looking at a couple of exceptional examples. Today I'll start class with this Bernoulli equation, then hopefully we'll look at the Riccati equation, and then finally the Clairaut equation. I'll give you an example of each. They're also in your homework, so this should help. Okay, so not these literal problems, but problem like them are in your homework, all right? And okay, so we make a substitution, and we trade our dy dx for what? For minus 1 over w squared dw dx, right? That's my dy dx term. This is that, right? Then I have plus what? 1 over x times y, which is what? Well, y is 1 over w, is equal to x over w squared. All right? The neat thing about this substitution for the Bernoulli problem is it's going to convert it into a linear differential equation in w. So we take this differential equation we got to, and what we're going to do is, what do you guys think we should do to this? What should we do? I multiply by w squared. I like that. I'm going to add a minus to your prescription here. So dw dx minus 1 over x times w is equal to minus x. So I multiplied by minus w squared, all right? Now we have a first-order differential equation in standard form, all right? And so we can calculate the integrating factor mu exponential integral of minus dx over x. That gives us, exponential of minus the natural log of the absolute value of x, which gives us, exponential of the natural log of the absolute value of x to the minus 1 power. So lo and behold, 1 over absolute value of x. Now, whenever you get absolute value like this in the integrating factor, you can just get rid of it because you're just trying to multiply by a function, right? And so if it's plus or minus something, you might as well just strip off the absolute value and we can just use 1 over x as the integrating factor here, all right? So we'll try use mu equals to 1 over x. That should work. So here we go. 1 over x times dw dx rather, minus 1 over x squared w is equal to minus x over x, also known as minus 1. So what I did right there was I took this differential equation and I multiplied by the integrating factor because that's what we do when we have a linear differential equation. We calculate the integrating factor, multiply by the integrating factor. What's the next step? The next step is the reverse product rule. So this is d dx of 1 over x times w is equal to minus 1. Now we're done because all we need to do is integrate both sides and we've solved the problem basically, right? So integrate both sides. I get w over x is equal to minus x plus a constant, right? Integrating. So now I can solve for w. So apparently w is minus x squared plus cx. But what was w? Remember what it was to start with? 1 over y. So that's equal to 1 over y. Can we solve for y? We'd like to find the explicit solution when we can. And we definitely can here because y is equal to 1 over cx minus x squared. And there you go. That is the solution to this Bernoulli equation. So to review, if you have a Bernoulli equation, you just make a w equals 1 minus y to the 1 minus n substitution. And when you make that substitution, it should give you a linear differential equation, which you can solve with the integrating factor method. And then after all that, you go back and undo the w substitution, which is, may or may not be more interesting than this, right? Could be that w is like y cubed or something, Then you'd need to take like a cube root, et cetera, et cetera. So that's a Bernoulli equation. This would be, in the practice homework, PP8. PP8 has 3 other Bernoulli equations and a kind of quick sketch of how you solve these. So next up is the Riccati equation. I'll tell you what that looks like. This one's interesting. Riccati equations, something like this. You're given dy dx equals to, say, p of x plus q of x times y plus r of x times y squared. Let's call this thing star. And y1 solves star. All right. If this is the case, it turns out that we can solve such a problem by making a particular substitution based on what we already know. All right, so we have a given solution. If this is the case, then the technique is to let y equals to y1 plus u to solve star. If you do this, you can find more solutions to it. So let me kind of illustrate it by example here. So it's kind of like we have one solution and we can use that one solution to generate more. This is a really new kind of phenomena in terms of the story we've been telling in here, right? I don't think we've experienced anything like this before in here. So this is kind of neat, different. But the steps we're going to make to solve this are pretty much the same ones that we've already been making, namely a combination of substitution, and then like linear equations, perhaps separation of variables. We'll see. Okay, so my example for us, example 2, is dy dx equal to 2 minus 2xy plus y squared. All right, that's the analog of star. And y1 equals to something solves this. Let me see if you guys can guess the solution while I'm adjusting the camera. Can you see something that would solve that? Can you guess it? If we could make these two things go away, right, then that would just leave us with dy dx equals to 2. dy dx equal to 2 has solution what? Y equals to 2x, right? Think about that. If I put 2x into here, I get minus 2x times 2x, which is minus 4x squared, and I get 4x squared. Hey, that works. So y1 equals to 2x is a solution. How did I find that? Well, I already know it, so it was easy for me to guess. Sorry, I'm an idiot. All right, so then basically you can identify here, you got like p equals to 2, q equals to minus 2x, r equals to 1, right? That's, making the comparison. This is, in fact, a Riccati type equation, right? Great. Now, the claim that I'm making is if we make a, so what's going on here? What's the substitute variable? So I'm making a u substitution, right? But it's kind of an implicit fashion. So we're going to try to find u such that y is equal to 2x plus u solves, I'm going to give this thing a name, Pac-Man. All right? So what happens if we take Pac-Man, right, and we feed it y equals to 2x plus u, what happens? Well, notice that dy dx is 2 plus du dx, right? So that means that, what does that tell us? Dy dx is what? It's equal to, well, dy dx minus 2 is equal to du dx, right? For one thing. So I can substitute that what I wrote is not wrong, but it's not going to help you guys. Let me just substitute and not try to be clever. Cleverness rescinded. All right, so just plug it in. We get what? Dy dx is 2 plus du dx equals to 2 minus 2xy, right? But y was what? Y was 2x plus u, and then plus y squared, which is 2x plus u squared. So that's making the substitution. What happens when we multiply this out, though? Well, the 2's, they'd be canceling, right? And what happens when I foil that mess out over there? I got a minus 4x squared minus 2xu plus 4x squared plus 4xu plus u squared. Well, lo and behold, these guys cancel, which is nice. And these simplify, right? What am I left with? I'm left with du dx, right? I have a plus 2xu there, so I'm going to move it to the other side, minus 2xu equal to u squared. What's that? Is it linear? No, this is a what? Come on, I showed you 10 minutes ago. You're supposed to know it for forever. It's a Bernoulli, right? This is a Bernoulli. I keep misspelling Bernoulli. Don't tell them. Well, anyway, so given this, I make a W equals to 1 over U substitution, right? Then U is equal to 1 over W, so du dx is minus 1 over W squared. This is the same I did in example 1, right? So that's going to bring me to a minus 1 over W squared dw dx minus 2x over W equal to 1 over W squared, multiply by minus W squared, like we did before. And that gets us to dw dx equals to, not equals to, minus 2xw equals to 1. Well, minus 1, right? Because there's a minus. Now we have found our way to a linear differential equation, right? The linear differential equation, how do we solve those? Integrating factor method, right? So, great. What's our integrating factor here? Yeah, so mu equals exponential of the integral of minus 2x dx, also known as e to the minus x squared. So we multiply the given differential equation by e to the minus x squared. E to the minus x squared dw dx minus 2x e to the minus x squared w equal to minus e to the x squared. All right. This looks like a 2-board problem. So, well, maybe 1.5 boards. So we got then ddx of what? ddx of, and I got an e to the minus x squared here. Is that right? Was there a minus 2x there? Oh, my bad, guys. Come on, don't let me do that. So you see something, say something. Say something. Is that minus right there? I had to multiply the black equation by minus w squared, right? So that minus cancels. So these are both negative in this equation. They better both be positive in the other one, right? These share the same fate sign-wise. You can't have minus minus and then minus plus minus over here. That's a plus, right? And as such, my integrating factor's got a plus 2x, a plus x squared here, okay? So the integrating factor was e to the x squared. I was about to discover that in the next step here, but okay, we e to the x squared dw dx plus 2x e to the x squared w. Now the minus on the right-hand side is real, right? So I've got minus e to the x squared there. All right, so once I fix that snafu, we have e to the x squared w equal to minus e to the x squared. Now what do we do? How do you undo a derivative? You integrate. So we just need to integrate e to the x squared. Do you remember that one? Do you remember anything about e to the x squared? No. That's a trick question. This one is a well-known example of a function which cannot be integrated by elementary means, right? So the best we can do here is to say, okay, so e to the x squared w is equal to minus the integral, let's say from x naught to x of like, e to the, oh my bad. Let me just leave this as an indefinite integral. Let me not be fancy. Minus integral of e to the x squared dx, all right, which tells me then that w is equal to minus e to the minus x squared integral of e to the x squared dx, right? And what was w? Remember, w was 1 over u, so this is equal to 1 over u. But what was u? U if you go back, was y. Remember, y was 2x plus u. Y was equal to 2x plus u. So we're actually trying to solve for y eventually, right? So this u is, well, we can also solve this for u, right? U is equal to y minus 2x, isn't it, right? So this means 1 over u is actually 1 over y minus 2x, right? So if I was just to underline this, I'd have an implicit solution to the problem, but we'd like to solve for y. Yeah, so let's do that. Solve for y. How should we solve for y? Let's flip it, right? So I've got 1 over minus e to the x squared integral of e to the x squared dx is equal to y minus 2x. Lo and behold, y is equal to 2x minus 1 over e to the x squared integral of e to the x squared dx, right? And if you want, we could make explicit, there's a constant, plus a constant here, just to, just to make explicit where the constant comes into play. It's right there.
Doesn't the first 2x have a negative on the x squared? Same thing. From the black to the blue.
Yeah, see here, why is there a minus on the x? So you're asking this right here. First of all, you're like, that's legit, right? Legit. Because we solve for w, so we multiply by the negative exponential there. And you're right, it shouldn't stop being negative. So let me make the corrections in red. Thank you, thank you. So that puts a minus here. And also here. And then I think we're good, yeah. So Riccati equation, this one example, it's got so much in it, right? More than like two substitutions. We got to see a Bernoulli equation, and of course also a linear equation. There's so much in this one example, so much. So my final interesting differential equation that we solve by a special method is called Clairaut's equation. So let me explain to you what those guys look like over here in a minute, after I clean the board. So I think the good thing about these substitution problems is they give us further experience in the basic methods, right? Every one of these you solve makes you stronger at like the more basic things like separation of variables and all those more basic things. But this is, so by the way, the Riccati equation was PP9 in the practice, problems. The Clairaut equation is PP10. So let's talk about this here. Clairaut, C-L-A-U-I-R-A-U-T equation. All right. So this one has the form y is equal to x y prime plus f of y prime. This is known as the Clairaut equation. So pretty much every one of these special equations, like my first order of business, is to share with you the sneaky trick that we use to solve it, right? Because it doesn't fall under the auspices of separation of variables or integrating factor technique. It's something else, right? And so this is like one of those. So here we have a function of y prime, okay? So the special observation here is that you can show that y equals to, so here's a claim, and we'll demonstrate it. It won't take us long, I hope. Y is equal to cx plus f of c solves this equation. So let me call this thing star. All right. And in addition, you can find parametric solutions. In addition, you can find x equals to minus f prime of t, and y equals to f of t minus t f prime of t, gives a parametric solution to star. All right. So maybe you guys can, while I'm adjusting the camera, can you see why that linear equation solves it? What happens when you, well, I already adjusted the camera. If I could remember anything, that'd be amazing. What happens if we plug the soon to be underlined in pink equation into star? What happens? Like what's y prime then? Yeah, y prime is c. So this, I'll write it up here, I guess. Y equals to cx plus f of c gives y prime equals to c. Hence, if we look at x y prime plus f of y prime, what do we get? We get x times c plus f of c, which is what? Oh, that's y. All right? So, yay. See what happened? I plugged in y prime into here, and out popped y, which is what we need. Plugging this equation into the right-hand side produced y, which is what it's supposed to do. So that's one thing. The other claim is that this is a parametric solution to this, to the Clairaut equation. How can we understand that? Let me suggest something. Let's look at y equals to x, and I'm going to write it out, dy dx plus f of y prime. Okay, that's the Clairaut equation, right? Let me rewrite this in Pfaffian form. In Pfaffian form, we can rewrite this as x dy plus parentheses f of y prime minus y times dx is equal to 0. All right? I'm deriving this claim right here. So, yeah. But I'm trying to give you an idea of like, what would you mean, how would you check something's a parametric solution to a given differential equation? Here's one way you could do it. If it is a parametric solution, it should be the case that if we take the differential equation like this and just divide by dt, right? If it's an honest to goodness parametric solution, when you plug it in to the parametrized form of the different, my argument is to you guys is that this is what I would call the parametrized version of star. All right? And I would claim that if we plug in, like you can, work it out. Like what is dy dt here? F, right? F prime of t. Product rule here, right? So minus f prime of t minus t f prime prime of t apparently, right? That's dy dt. And what's dx dt for my parametrized solution? So I'm differentiating. Hope you guys keep track of what I'm doing here. So I'm calling this thing ghost. So here I'm differentiating ghost, so to speak. What's dx dt? Well, that's easier. We're just differentiating f prime. So we've got minus f prime prime. of t. And the claim is that if you plug these two equations I just found, right, if you take this, right, and you were to shove it up into there, right, and if you were to take this over here and shove it up in there, and you were to put what we gave x being minus f prime of t and over here, oh goodness gracious, well you got to put in the, I don't want to do it. Anyway, it's true. All right, so you can, enough. We've suffered enough on this claim. Let's look at an example. Yes. You don't have to believe me that the parametrized solutions work. I mean, we're going to see that they work. But here's the rough thing. The parametric equations, they may actually provide you extraneous solutions to the Clairaut equation, as it turns out. So, all right, let me try to wrap this up here. I don't want to spend forever on this problem. Come on. Nope. Come on. Here we go. This example 3. We have y is equal to x, y prime, plus 1/2 y prime squared. So this is, in fact, a Clairaut equation, right? So this is Clairaut. I can't spell this stupid thing. Yeah, well, anyway, you got it. C equation. All right, there we go. With f of y prime equals to what? Not 1/2, not minus, but just 1/2 y prime squared, right? That's the function of y prime there. Yeah? So this means that we find solutions. Y equals to what? Kind of silly. Cx plus f of c, right? Cx plus f of c. What is f of c here? Yeah, Cx plus 1/2 c squared. How about the parametric? How about the parametric solutions? We have what? X equals to what? Minus f prime of t. So it might be helpful for me to rewrite this as in kind of a dumb way. F of x equals to what? 1/2 x squared, right? If I write the variable as x for the sake of not losing you guys. So f prime of t here is what? Minus, so what's f prime of x? Yeah, x. So you're integrating. It's all good. Okay, so x is equal to minus f prime of t would be x is equal to minus t, right? And how about y? Y is equal to f of t minus t f prime of t, which is what? So we've got 1/2 t squared, right? Minus t times what? F prime of t, what was it? Oh yeah, t. Just minus t squared. Okay, so this is actually minus 1/2 t squared, right? So can we rewrite this as a Cartesian equation? Like we've got x equals to minus t and y equals to minus 1/2 t squared. We can eliminate t and find the Cartesian equation for the solution, right? What is it? It's just minus 1/2 x squared, right? Because I can plug the t equals to minus x in, I square it, minus goes away, I'm left with that. So is that actually a solution to, is this actually a solution to, like, these are honest to goodness solutions to the given Clairaut equation in this example, okay? Like these are legit solutions for truth. Is that one? I mean, go back to the original equation. Does it work? This says it's not. He says, it says the book I got it from, it says one can readily see that this function is not part of the family 9, the 9 being the purple box thing. So allegedly, if I tried to plug that back into here, it wouldn't work. So, I mean, I get minus x squared from the first term, and then I get 1/2 it seems like it works to me. I don't know. I'm not seeing that it doesn't work. There's something slipping past me here at the moment. But I'd like to just take a second here to talk about this, what this looks like geometrically. There's something really cool. What's going on here, this minus 1/2 x squared is like this, right? And it's kind of fun to actually draw what's going on. Because these equations, like, for example, put in c equals to 0, what do you have? Yeah, y equals 0, so that's this one, right? There's c equals to 0. How about c equals to 1? X plus 1/2. So let's see here. And so that, yeah, I think so that's going to be 1/2. So anyway, what ends up happening if you graph it, it's like this. So like all of this family of solutions, they all sort of lay over that exceptional solution and like kind of envelope it in that way. So that's the geometry behind this differential equation, which is kind of pretty. But anyway, this is just an example of another solution technique. Here is the attendance sheet, lest I forget. Could you add a date for me? Just right there. Scoop. All right, so I think I might even have other examples in the notes if you look that I haven't covered in here of the, the Clairaut and the Riccati equation. But I think that's enough for us in here. So I'm going to turn the page in here, so to speak, and look at the question of exact equations. And I want to show you a really different way of thinking about the problem of exact equations. So I'm going to use some calculus 3. All right, I'm going to start with some calculus 3, and I'm going to end with some things you probably haven't seen before. So hopefully you'll find it interesting. I may or may not get through it today, but we'll get started on it at least. So the first question I want to address is why is it that if we meet the closed condition, why is it that if we meet the closed condition on an exact differential equation, why does that assure us that there exists a level function whose level curves are the solution to that exact equation? All right, so that's my starting question. Okay? We've seen that that works out that way, right? But I haven't proved to you why that's the case, and I want to do that now. So here's the theorem. If m dx plus n dy equals to 0, where m, let me write it out, partial m, partial y is equal to partial n, partial x, on a simply connected subset U of the plane, then there exists f such that df is equal to m dx plus n dy, and hence f of x comma y equals to a constant solves star. So that's the claim. So I'm going to give you a proof here that uses calculus 3, and here's my proof. Let f, let me not use f, let's use g. G vector equal the vector field m comma n. All right? Then let me be a little bit lazier. Let me use three-dimensional calculus 3. M comma n comma 0. There we go. All right. Then the curl of G is equal to what? Remember the end of calculus 3? You were there. You saw these things. So the curl of G is, partial y g z minus partial z g. Let me use number. Well, it's fine. Gz, gy. These are not partial derivatives, obviously. I'm writing the partial derivatives as partials. Partial z gx minus partial x gz, comma, partial y, and partial x rather, gy minus partial y gx. This is the curl. Of course, immediately you notice that gz is what? So gz is 0. My g sub y is n. My g sub x, the x component of g, is m. All right, that's the notation I'm using here, okay? So some of these derivatives are super easy, right? There is no z dependence, right? Because we're just a function of x and y. There's no z dependence to be found. And the z component's 0. So this, 0. This, 0. And how about the last one? This we're assuming is 0. This is 0 because we assumed, I need to give it a name, Pac-Man. Right, this guy right here. That was in our assumptions. Therefore, G has a curl which is 0. Right? but there's a theorem of calculus 3, which says that if you have a vector field whose curl is 0 on a simply connected domain, that tells you something about the vector field. Oh man, I never moved my camera. Goodness gracious. I'm the worst cameraman. Fortunately, no one's at a career fair right now, so no one will notice. That's a joke. We're missing some people. Apparently, employment's more important than my course. Ooh. No, just kidding. It's good. If you guys have an appointment like a job interview or something, feel free to skip my course for a job interview. That's fine. Just watch the video later. It's cool. So the curl is 0. We had a theorem in calculus 3, which then says, so if, but curl of G equals to 0 on simply connected domain means G is conservative. Which is to say, there exists little g, let's say, a mapping from U to R, such that what? Such that the gradient of little g is equal to big G. Now I'm cheating a little bit because I'm using three-dimensional stuff to do two-dimensional stuff, but you'll forgive me. But what does this mean? This means big G is equal to what? Partial G, partial X, partial G, partial Y, partial G, partial Z, generally speaking. Of course, this part, for my given application, this is 0 because of, we had GZ equals to 0, right? I mean, there is no Z dependence to the potential function G here. But what is this G? What is G? It's exactly a function whose partial derivative with respect to x is m, and whose partial derivative with respect to y is n. In other words, I'm just saying, so apparently, little g is the f that we want, right? Because dg is partial g partial x dx plus partial g partial y dy, which is indeed m dx plus n dy, given our constructions. It was important that we're talking about a simply connected domain. All right? So there's a proof by some calculus 3 that you might be a little bit rusty on, but that's pretty much it. I mean, there's more that you can do, right? You can, if you have the closed condition, there's a family of connected ideas, right? A conservative vector field is one who's equal to the gradient of potential function. It's also one who the line integral around a loop is 0. It's also one that has path independence of the line integral, right? And you can use that path independence to construct the potential function by integration. That's essentially the heart of that exact equation theorem I shared with you like last week. All right, that's why that formula is what it is. But now I'm gonna do something that you probably didn't see in calculus 3, which is I'm going to introduce you guys to something called the exterior calculus. And you might say, what's the exterior calculus? Well, I'm glad you asked. I mean, I made you ask in my mind. You may not actually be asking this, but you should, because it's interesting. So, exterior calculus. So, I'm going to do it in 3 dimensions because it's most interesting there, and then we'll apply it in 2 dimensions to gain further understanding of differential equations. At the end of the day, it just gives us a simple additional way to understand that closed condition. All right? But also, this gives you a window into the calculus which is used for dimensions beyond 3. So let me get straight to it. Let's just do it in R3. All right? So I'll be real brief. You have 0 forms, you have 1 forms, you have 2 forms, and you have 3 forms. 0 form is just a function, like g. Just, a function of x, y, and z. All right, just a plain old function is a 0 form. A 1 form is something like a dx plus b dy plus c dz. You have extensive experience working with 1 forms in Calculus 3. We learn how to integrate these things. In fact, they correspond uniquely to vector fields. So we'll do like omega subvector ABC. So this is the so-called work form correspondence. You give me the vector field ABC, I give you the 1 form, a dx plus b dy plus c dz. This is the deal. There are 2 forms as well. So if you have like a dy wedge dz, you're like, whoa, what happened there? I'm introducing something called the wedge product, so stick with me. So think of the wedge product in a somewhat formal sense. It's something we can do with 2 differentials to get a new object, which is called a 2 form. It is not anything you've seen before, perhaps, right? It's the wedge product of 2 differentials. It's a 2 form. This is what's known as the flux form of the vector field ABC. So this is the work form correspondence. This phi is the flux form correspondence. And 3 forms, well, they're kind of boring. There's just one of them. H dx wedge dy wedge dz. That's all you have. The wedge product is very much like the things you already know. So a differential form, generically speaking, it's any one of these things. All right? And so if you have, say, alpha, beta, and gamma are differential forms, then we have the following things, like alpha plus beta wedge gamma is alpha wedge gamma plus beta wedge gamma. We also have alpha wedge beta wedge gamma makes sense. What I'm trying to say there is that the wedge product is associative. All right, it's associative. Now, the wedge product is also, you can also like pull constants out, If I had let me throw a constant in here. Like if I put a constant here like this, I could pull it out here like that. Right? You can pull constants out. The wedge product, on the other hand, is not commutative. It's something a little bit different. So the way it works is this. If we have alpha wedge beta, it's equal to -1 to the degree of alpha times the degree of beta, beta wedge alpha. So this is the graded commutivity of the wedge product. So the degree is what I listed here. So like degree 0, degree 1, degree 2, degree 3. So like fundamental, fun facts, all right? See, these things are basic. Dx, wedge dx, is equal to minus dx wedge dx. What's that mean then? If dx wedge dx is equal to minus dx wedge dx, then what? What does that say about dx wedge dx? I mean, apparently it says 2 dx wedge dx is equal to what? Well, no, not -2, but if I add dx wedge dx to both sides, I have twice dx wedge dx is 0. And so this is one of the fundamental things about the wedge product, is if you have any differential that's repeated, it wedges to 0. It's like the cross product, right? The cross product of any vector with itself is 0. So on the other hand, we have like dx wedge dy is minus dy wedge dx. But you might say, well, wait a minute, is this just the cross product? Is this just the cross product? It's something somebody will ask once they understand what's going on here, right? And the answer is no. See, because with the cross product, if I had for instance, if you like the notation I cross j, they're unit vectors, right? I cross j is what? K, right? But dx wedge dy, it's not dz. It is a two form, dx wedge dy. It's equal to minus dy wedge dx, that's true. In some sense, geometrically, it corresponds to like a little area with a little bit of dx and a little bit of dy. So you can think about one form's kind of corresponding to line segments. You can think about two forms kind of corresponding to little area segments. You can think about three forms kind of corresponding to little volume segments, right? The larger program I'm describing here is called geometric algebra, which is not something I know. People who really get into it have a kind of religious devotion to it. I don't understand. But, but this is nevertheless interesting. The reason that this is called exterior calculus is that we're taking two objects and we can take their product and we get a new object. So like, for example, if I take ADX plus BDY, well, let me make it simpler here. Say we take dx plus 3dz, and I take the wedge product with, oh, I don't know, dy minus dz, all right? So the way this works, you just distribute like usual, and you use the fact that if you have any repeat, you get 0. So this gives me like dx wedge dy, and then minus dx wedge dz, and then I get plus 3 dz wedge dy, and I think that's it. See, because dz wedge dz is 0. All right? So check this out. Another way to look at this is we have the work form of the vector 1, 0, 3, wedged product with the work form of the vector 0, 1, minus 1, right? And it turns out that's equal to, let's see, do I have the right pattern? I've got dy, I gotta be careful here. I'm supposed to have dy dz. I got one more step here, then I can make my comment. So this is, let me put them in order. So this is minus 3 dy wedge dz plus dz wedge dx plus dx wedge dy, all right? Now I put them in the matching order here. See, the order matters. So if I do that, you can identify then, according to the definition I just made 3 minutes ago, so you know it. It's a joke. That's the flux form of minus 3, 1, 1. Try this out. What's the dot product of this vector and this vector? What do you get? 0, plus 1, minus 1. Hey, 0. Take the dot product of this vector with that. What do you get? Minus 3. Right. What is this? It's a vector which is perpendicular to both of the vectors we're finding the work form corresponding to. That's the cross product. It's the cross product. So if this is A and this is B, this right here is A cross B. And indeed, this is a general relation of the exterior algebra, which is the wedge form of A with the work form of A wedged with the work form of B is in fact the flux form of A cross B. So in this way, the wedge product folds into it the cross product. The wedge product does calculate the cross product in this way. All right? That's one thing. If you were to take the wedge product again, I won't prove this to you, but you could try it out for yourself. If we take omega A, wedge omega B, wedge omega C, what you get is A dot B cross C times dx wedge dy wedge dz. All right. We don't actually need too much of this. I just wanted to give you enough to have a sense of it, all right? Now I'm going to turn to calculus. So every one of these differential forms that I've introduced you to